All right, guys, so this is video number 2 for our Newton's second law lab on rotation and moment of inertia. And now we're at the point where we need to derive a formula for moment of inertia so that we can collect the proper data and calculate our experimental moment of inertia. All right, so here's my apparatus. I've got a little schematic drawing here. Here's my pulling mass that's attached to a string. And the string goes over what we're going to consider a massless frictionless pulley. And that provides the tension, or excuse me, the torque to rotate the apparatus. All right, and if we do a free body diagram for our pulling mass, we realize that there's only two forces acting on the pulling mass. There's the force of gravity pulling down, and there's the tension of the string pulling up. So applying Newton's second law, we've got mg minus the tension, because of course mg is going down, that's in the direction of acceleration, and so that's the positive direction, and tension's pulling up, and that's equal to mass times acceleration of our object here. And if we rearrange for the tension, what we get is the tension is equal to mass times gravity minus mass times acceleration. Okay, so our tension is the torque. That is the force that causes this to rotate. So we have two formulas for torque. We have that the moment of inertia times angular acceleration is equal to the torque, and that the force, in this case the tension, times the radius perpendicularly is equal to the torque. And remember, torque is the force that causes rotation. So what we're going to do is we're going to combine these two in order to get a formula for the force that causes the acceleration. So I've rearranged the two formulas. Here I've set them equal to one another, and I've rearranged for force. And this is the force that the tension of the string provides. So we can combine these now, right? Now we can say that the tension, which is really the force for rotation, is equal to moment of inertia times the acceleration divided by the radius. And now I have these two, that I have two different types of accelerations, and I need to use the linking formula in order to get rid of angular acceleration and just get it down to linear acceleration. Once I do that, I'll be able to calculate the moment of inertia. All right, so after you do that, you can then run your apparatus. Now, a couple of things, you guys. And I'm just going to take this and put this up. I don't know if you noticed, but this thing actually rotates very rapidly. And so earlier today, I saw a few of you try to use a very large mass. Start with a small amount. If you go with too large amounts and you go too rapidly, then you're going to have a hard time timing, but also your nuts are going to move off the arms and you won't have the right radius. Once you've collected your data, then you're going to want to create a graph, and I'm not going to show you too much about this graph, but from the graph you should be able to get your moment of inertia also, and then you can see how close you are to your theoretical value. Good luck. See you in class.